Welcome to 1007 ICT, 1807 ICT, 7611 ICT Computer Systems and Networks. This is Lecture 3B, Digital Logic and Digital Circuits. So last time we covered digital logic, the basic logic gates, Boolean algebra and combinatorial logic gates. And really what we covered was the AND gate, the OR gate, the NOT gate, the NAND gate, the NOR gate, and XOR. And we sort of saw how those things work. And the basic idea with a logic gate is you have some inputs, you push it through a box of some kind of gate, and it gives you an output of some kind. And depending on what box you're using, and or not and so on, you'll get a different outcome. Alright, so we need to learn what the truth tables or the different input and output combinations for each logic gate are. So in this lecture we'll be looking at the logic unit, selection logic, decoder logic. They get more complex very, very quickly. They're still fairly simple things that we're going to look at, but it will take a little bit of effort to sort of see how all the things flow through, because there's now going to be more than one gate that we're dealing with. We'll also very quickly look at multiplexing and demultiplexing. So at the end of this lecture you'll have gained an understanding of this selection logic, decoder logic, multiplexes, demultiplexes, and half and full adders. Now what I'm just going to point out with this stuff is that this will be relevant to your assignment, so the more you can sort of play around with this and practice it, the better it will be, and you'll get plenty of practice in the workshops as well. So last time we ended at this slide with the logic unit, and what we wanted to do was make something called a programmable logic that lets us take some inputs and process them in some way with AND, OR, XOR, NOT gate, for example, have multiple answers that we can deal with, and then choose one of those answers. And we might choose this particular answer this time, and the next instant we might choose a different answer, and so on, right? So we can just choose which of the outputs we actually want. So what we're actually describing there, so I'll give you a visual of this, and you're very familiar with this, I'm pretty sure. This is a box, right? It has a big dial on the front, and it's some kind of amplifier or thing that selects inputs. So you might have a CD player, you might have a DVD player, you might have a TV, you might have, I don't know, your phone, right? Whatever the different inputs are. And what you can do with this this dial is all of those devices may be working at the same time, but you don't want them all at the same time. You can only listen to one at once, so you might have it set to TV at the moment. Yep. Later, you might say, well, actually, I want the DVD now. Right? So what are we doing with this big knob in the middle? We're selecting, or we're choosing, switching. There's lots of different words you could use. Our logic unit does the same thing. Imagine that this is the AND gate. This is the OR gate. This is the NOT gate. And I don't know, let's say this is XOR. Yeah? We can just choose between each of those functions. So you have a model for this already. It's just, this is at a much, much lower level. Right? Okay, so that's really what we're doing with this logic gate. So if you look at the logic gate, you'll see that there are four, so if you look at the logic unit, there's four logic gates, AND, OR, XOR, or NOT, and then there's that yellow box. The yellow box is actually where all the magic happens, where you choose which one you're actually going to use. So here is our logic unit. I mentioned this yesterday. You got two inputs, A and B. A goes into the AND, it goes into the OR, it goes into the XOR, it goes into the NOT, and then B also goes into the AND, goes into the OR and the XOR. It doesn't need to go into the NOT because it only takes one input. So what we've got is those two inputs are going into all of these gates at the same time. Each of these gates gives you an answer. So A and B will be something. A or B will be something else. Yep, they're all different outputs. So you'll have how many outputs? 1, 2, 3, 4. They come into this box on this side. The box does something. You select somehow, and then you get one output, the one that you chose. You notice there are two selection lines down the bottom here. I mentioned yesterday as well that with two lines I can have these cases, 0, 0, 0, 1, 1, 0, and 1, 1. Right? They're the possible cases for two lines. Lines can be on or off. So they represent bits, actually. There are 2 bits down the bottom here. So if we label this one 0, 0, this one 0, 1, this one 1, 0, and this one 1, 1, then if I give you 1, 0 on the input lines, like this 1, 0 here, which one am I choosing? XOR. XOR will go through. What happens to AND, OR, and NOT? Somehow they get stopped. Yeah? They don't interfere with the output. Is the idea pretty simple? Do you think the logic is that simple? Probably not. There's probably something complex going on underneath, but the basic idea is fairly straightforward, I think. That's what we're trying to achieve. So the next section is us trying to achieve that. And actually, what we're going to do is we're going to focus on this box. What does this box do? How does it do its job? There are two parts. The first part is, well, just select which one you want, right? We're going to choose one, so there's a selection logic. This part here, down the bottom, complicates things. You notice I have two lines, but how many different combinations do I have? 4. Is 2 and 4 the same? No, there's a difference. So I have to take this. This is a compressed version of the total values I can have, and I have to uncompress it in some way. All right, we call that decoding. So there's a decoding process that has to happen. I'll give you 2 inputs, and I have to decode it into 4 outputs in this case. Yep. Okay, so just keep that in mind when we go through these examples. So we have something called selection logic, and basically, if we have a number of inputs, in this case we've got 4, A, B, C, D, and we want to select one of them to use in a logic function, we have to do a bit of work. It doesn't happen automatically. So we need a special function to switch the selected input into the output that we want, and then we have a couple of S lines down the bottom. So you'll notice the S lines. Have you seen a word starting with S previously? Selector. Yeah, I've mentioned that already. So we're going to select some things. I'll show you a Logisim version of this, but just have a look at the diagram here. You'll see A, B, C, D on the left. What other gates are on the left? Those big D-looking things. They're AND gates, right? So I'll give you an insight into AND gates. AND gates only let through a 1 if both inputs are 1. Yeah? They actually block things for the most part. Their job is to stop things going through in one sense. Would that be useful in this environment? Yeah? 3 of those AND gates out of the 4 will say stop. One of them will say sure, go. How do you get an AND gate to let something through? 1 on both sides. Yeah? So there's an input A, and there's the bottom is turning things on and off, basically. That's how this kind of works. I'll show you an example in a second, though, to make that clear. What's on the right-hand side? What kind of gates? The pointy ones. They're OR gates. And OR gates collect things. They group things together. They let things through, actually. Yeah? As long as you've got a 1 anywhere, there's a 1 on the output. So the first row, the A, B, C, D, those AND gates, they stop things from going through. One of them will let something through. What about the OR gates? Well, once something comes through, you want to know about it, so you let that one through. Okay, that's how that works. So there's an example here, and what we're saying is, look, we've got some input coming in here, 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 and here. I don't really care what that input is. The input can be a 0 or a 1, yeah, for any of these. The only way that one of these guys will let something through is if, let's say, S2 goes to a 1 and these other ones are zeros. What happens to here? You get a 1 coming in here. This will be a 0, a 0, and a 0. Yep. So this one won't let anything through, this one won't let anything through, that one will not let anything through. S2 though, what is it saying? Well, this side's fine. It could let something through. If my answer is a 1, we get a 1. Would you agree? If my answer is a 0, we get a 0. Does that match my input? Yes. If I got a 1 coming in there, I get a 1. If I got a 0 coming in there, I get a 0. Okay, so that's just as a diagram. It becomes much nicer when we start working with Logisim. So Logisim is this piece of software. We can basically draw circuits with it. This is a complicated circuit. Let me just quickly draw you a really basic one over here. Right, so I'll put some inputs onto my circuit. So I'm just drawing a very simple circuit here just next to it. It's not going to be very neat. So what I'm doing at the moment, I'm putting some inputs in. I'm drawing some wires. So there's 2 inputs on the left, and then there is an output on the right. And I'm just going to focus on this section here for now. right? To ignore the bit on the top left. And I'm just going to show you, look, this is an AND gate, right? The inputs at the moment are 0 and 0, so the output is 0. The input is 1 and 0, still 0, 0 and 1, 1, 1, the light goes on. That's how it works. So we can now visually see how these things work. So that's actually really nice. So like I said, I just wanted to illustrate that part. You'll see that there's obviously a much more detailed circuit here. What circuit is this? We've seen it just before. We called it selector circuit. Yep. And so you'll notice here are my A, B, C, D. These are my inputs. Where do they come from? Let me go back to here. This is A, this is B, C, and D. You see how they're related to each other? So this yellow box that we're working on has a selector inside it. Okay, and the orientation is the same. So these are the inputs, A and or whatever the other one was, and then not. These guys here, you'll notice they're all zeros. There must be some rules about which ones of these are ones and which ones are zeros. Would you agree? What's the rule, do you think? The two inputs to the selector box will determine which one's on. And what we need to do is make sure that only one of these is on. So either this one is on and everything else is off, or this one is on and everything else is off, or this one, or this one. Can you have this situation? No, because it's broken. What you want is just one of them. Can you see where a decoder might come in to kind of work out which one to turn on and which ones to turn off? That's the next part. Okay, so at the moment, let's assume that, I don't know, we'll pick this one, the top one. You'll notice that it doesn't matter what I do to B, in this case, or C, or D. Yeah? We're just getting 0. And why are we getting 0? Because this one is turned on, and the input is 0. So it matches A. What about if I make A 1? The 1 comes through, so it matches A. Will this always match A? Only if S0 is on. If S1 is on, which one will it match? B. Yeah? So what we've got here, and again, you want to try this out, play around with this, see how this works. But what we've got here is a circuit that allows us to get 4 inputs and choose one. Yep. And it does that by having these AND gates on the left, and the AND gates block things, and then these OR gates on the right, these guys, they combine things. Right? They put things back together. So that's the selection logic. That's the easy part in some sense, at least conceptually, right? Just thinking about that. The process, what it's trying to achieve is, I think, pretty straightforward. You've got 4 things coming in, you choose one, you let one of them through. The next part is this decoder logic. Now this is more complicated. And part of the reason it's more complicated is because we're taking 2 input lines and we're converting it into 4 outputs. There's a conversion process that has to happen. The reason we do this is, you remember when we're working with CPUs and things, we have a limited amount of space. If I have a complex computer, like the one I showed you there, you got AND or NOT, right? I think X or whatever the different gates were, right? There's 4 gates. Is that like my laptop, do you think? Do you think my laptop has more things it can do? Absolutely, right? So you might have 128 of these things, or many, many more of those different functions. So if you have many, many more of those functions, then you need many more input lines. Okay, so if you have 100 functions, let's say, you would need 128 or 100 input lines at the very least. Does that make sense? So do you have enough space on your chip to do that? Probably not. You want to compress it. So if I have 100 inputs, I can do that with 8 input lines. Actually 7. I don't need 8. So I can drastically reduce the number of inputs. So to do that, though, we need a compression. And when we compress it, it means this circuit is more complicated because we have to uncompress it. All right. So how does this one work? Well, if you look at this table, you'll see if my inputs, there's S1 and S2, they're my 2 lines. Then it goes through all this circuitry here, and eventually one of these will be on. Let's say it's this one, or it will be this one, yeah, or the 3rd one or the 4th one. So that logic is turning 3 of them off and turning one of them on. Yep. Let's look at this table. When it's 0, 0, S1 is 0 and S2 is 0, which one is on? X0 and the other ones are off. When it's 0, 1, which one is on? X1 and the other 3 are off. When it's 1, 0, it's X2, the other 3 are off, and 1, 1 off and X3 is on. Looking at that table, is there always only one output on? Yes. And they're organized in a particular way. There's some logic here. Do you remember these from yesterday? These statements? What do you think we're going to do with these statements? Plug some things in and just verify that it's true. These statements together should create this table. That's what we're saying. Okay. So at this point, I'll take you to this is the actual Logisim version of the decoder. You'll notice at the moment I have 0 and 0 and X0 is on. Okay? I'll point out something about these. The order of these is very important, and the order of these is opposite to what is on the slides, right? Or at least opposite to what you might expect. So this is 0, 1. You notice that X1 is on, and the other ones are off. That means that this is 1, 0. That's this one, and then what about 1, 1? Yeah? So if you look at this, you'll see these two NOT gates. So sometimes we're applying NOT, and sometimes we're not applying NOT. Okay, looking at the diagram here, here are those statements. Let's work through those. And what did we do last time with these statements? We plug some values in. So what values do we have? Well, S1 can be 0 and S2 can be 0. Would you agree? That's the first state. If S1 is 0 and S2 is 0, what's not S1? 1 and 1. The reason I've got all four of these laid out like this is because my statements will use some combination of S1 and not S1 and S2 and not S2. So it's just easy to have a look at them. So let's look at the first one. X0 is not S1 and not S2. So not S1 and not S2 is 1 and 1, which is 1. So the answer is 1. Okay? So let's look at the next one. We're still in S1 is 0 and S2 is 0. And the next statement is not S1 and S2. You see the second one here? So what's this? 1 and 0 is 0. So we're still in S1 and S2, and this one is the third one, which is S1 and not S2, which is 0 and 1 is 0, so the answer is 0. And the last one is still 0, 0. This one is S1 and S2, and that's 0 and 0 is 0. Can you see what I've done here? I've got 1, let me draw it over here, 1, 0, 0, 0. This is one row of my truth table. So if I look at my truth table here, which one have I done? Actually, I'll just go back one. I've done, it might turn out to be an AND, by the way, as a gate, but what I've actually done is this row. You notice for S1 and S2 being 0, 0, I've computed these four statements, and they give me these four values. Can I do the same thing for 0, 1? Yeah, I'm not going to. That's way too much working out. You can try that out for yourself, and you will generate this table, right? And what's the benefit of generating this table? Why is it important that we generate this particular table? Well, for us to verify the circuit works correctly, that's correct. But really what we want is this circuit to have only one output on for any given two inputs. Not two, not three, but just one output. Should it be a different output for every set of inputs? Yes. All right, so we're verifying that it works, but it's necessary that it works like this because we need to be able to turn things on and off appropriately. So that's the decoder logic. It's a little more complicated, would you agree? And the reason it's complicated is because we're doing something complicated, right? We're taking two inputs, in this case, turning into four outputs, one of four outputs. By contrast, the selector was much easier to think about, right? So you'll see that fairly frequently, that some things are actually simple to think about, some things are a little bit more challenging to think about. So how does it work? Well, this multiplexer, that's what we get when we put the decoder and the selector together. You'll notice this is a much smaller truth table. You'll see on the truth table on the left, 0, 0 gives you A. 0, 1 gives you B. 1, 0 gives you C. And 1, 1 gives you D. We've compressed a bit of information there in that truth table. Yeah? But if I'm looking at a multiplexer, what I want to know is, well, how do I get the A input? And what do I have to give the selection lines? 0 and 0. If I want to get the B input, 0 and 1. Okay. So here is a multiplexer. Can you see the different components that we have here? Do you remember when we first started, we had our logic unit? That's this part, yeah? And then we had this yellow box. And the yellow box is this thing, the selector, and this thing, the decoder, plugged together. Can you see how they're related to each other? So the logic unit, or the logic, gives you a value into your selector. And then the decoder down the bottom says, which one do you want to turn on? Yep. So at the moment, which one is turned on? 0, 0 gives me X0, which means the top one. Yeah? So only AND will do something for me in this case. So for example, nothing, nothing, and I should get a 1. Does that make sense? None of the other gates at the moment are allowed to go through their AND gate. They're just stopped. How do I change that? Well, I change one of these guys. So let's just pick this one, and you'll notice this one, now the third one is on, and it just so happens that XOR is 0 at the moment, so let's change that. XOR is now 1, and that gate goes through. What I want to point out here is that if you first look at this this diagram, it's very busy. There's a lot going on. Would you agree with that? It's difficult to see what's happening. I didn't show you this diagram first. I showed you the individual parts. So when you're working with this stuff, work with the individual parts first and build up. Right? It's going to make things a lot easier. The other thing I tried to do there was show you what the intuition behind this circuit is, what it is that it's trying to achieve. Right? Rather than going into the specific details, just say, well, this is trying to say, let one of these inputs go through, and that will also make it a bit easier to think about these circuits. So that's a multiplexer. You notice the yellow shape there? Is that the same shape as this one? Yep. And you'll notice here the selector is yellow, the decoder is yellow, and then we put them together. You might have to rotate them to make it sort of look nice, but when you go through these, just have a look at the shapes and the colors. They kind of identify which parts belong to what you have to build. We also have this idea of a demultiplexer. So multiplexing is taking some inputs and giving you one output, for example, that you choose. Demultiplexing is taking multiple inputs, one input and giving you multiple outputs. So this one's a little bit more difficult to think about, but imagine, I don't know, like you've got a house, right, and you've got a stereo in one of the rooms in the house, and then you've got speakers in the living room, you've got speakers in the kitchen, you've got speakers in the toilet, right, wherever you are, you have some speakers, and you can turn on the speakers in a particular room. How many sound signals do you have? You've got one sound signal, but you have multiple output devices, and you can choose which one you want. That's a very similar kind of model to what we're talking about here. So this is called a demultiplexer. You see there's one input coming in, and then you choose which one of the outputs you want. All right, as I said, it's a little more difficult to think about, but the speakers in different rooms in the house with one sound signals probably works all right. Then we move on to something called a half adder. So you remember what we did in lecture 2? We did addition, and we worked out it wasn't actually that difficult in terms of, we already know how to do it in base 10. We actually need some circuitry to do this, and the circuitry may be a little more challenging, right? Because the machine doesn't actually understand numbers. doesn't even understand ones and zeros. It works with electricity, right? So we have to set things up so that our logic gates, our logic circuits, are doing the thing that we need them to do to get the right output. That's one simple way to look at it. So we can also create math functions, and the simplest math function is the half adder, and this thing can add 2 digits or 2 bits to give a sum and a carry bit. Apparently, looking at the bottom there, there's a XOR gate and an AND gate that comprises this half adder. So I'll show you how you generate that, or how you can think about this. So when we're working with 2 digits, so let's see how we did this before. We did 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And then 1 plus 1 is 0. Carry the 1. Yep, so we have 1 here. Let me relabel this. I'm going to call these guys A, these guys B, and this is the sum. Okay, so let's have a look at why I'm doing that. So here's A, here's B, here's the sum. Okay, so A is 0, B is 0. A is 0, B is 0. The sum is 0. A is 0, B is 1. The sum is 1. A is 1, B is 0. 1. A is 1 and B is 1. 0, and then I need an extra column for the carry. There's a carry of 1. Does that make sense? That means that in these other ones, the carry was 0. There was no carry, actually. There was still a column, but we didn't have to deal with it until this last case. I've got a truth table. What can I do with truth tables? They represent logic gates. So I've taken some maths, turned it into a truth table, and now I can use it to generate some logic gates. So how do we do that? Well, let's have a look at this guy. The sum and the carry, they're the 2 output columns, right? They're the things, take the inputs and you process them and give you an output. So the sum, let's look at the carry. I think the carry is the easiest one. What gate is this? This is an AND gate. So my circuit will have an AND gate in it. And actually, it will have an A and a B. And I'm just going to draw it like this so we keep it the same as the diagram that's on the slide. But we'll see here, we've got an A and a B, and this is the carry. Yep. If I have a 0 and a 0 coming in, the carry will be 0. 0 and 1, the carry will be 0. 1 and 1, the carry will be 1. So this is an AND gate. What about this sum column? This one. This is an XOR gate. Yep. So here's an XOR gate. A and B. And this is the sum. So what I did was I looked at the structure of my maths that I wanted to represent. Does it matter what this is? Doesn't matter, right? It could be any mathematical function. I've looked at what it looks like in terms of the inputs and the outputs, and then I built my truth table, and from that truth table I can derive some gates. I can work out, okay, look, this column here, oh, that matches as XOR. Does it always match that nicely? Probably not. I might have to do some manipulation to it to get the right output, but this one was nice and easy. Now this is called a half adder. The word half suggests something. What is that? It's not a full adder, right? So it does half the job. And the reason it does half the job is because you'll notice with all of these cases, 0 plus 0, I can also have a carry in coming in. So I've got to carry out, that's fine, but there's also a carry in, which gives me some other cases. In particular, this case. Yeah? This one has how many ones coming in? 3. How many inputs can my half adder take? 2. You cannot do this computation. This line, this red line here, you cannot do this one because you don't have the facility to add the extra carry coming in. So what's the solution to that? If I read this, I'll say, look, it's 1 plus 1. That's this one, right? That's this guy. And then what do I do next? I add one more, right? So if I could have a C input coming in here, a carry in, for example, if I could plug that in somehow, that would fix my half adder problem. We can't just fix it like that. What we actually have to do is we have to use something called a full adder. But this is the slide describing that. I just went through the description, by the way. That the problem that we have is that we don't have the carry in, and so when we want to add things in, we need actually this guy here, the full adder. So you'll see here the full adder. What does it look like? It's two half adders, actually. So the first half adder adds the first two parts, the A and the B, and then the second half adder says, okay, you've got an answer, now add the next carry in part. And then there's an extra OR gate. What did we say OR gates do for us? They combine things. AND gates block things, OR gates combine things. How many carries do we have with our two half adders? There are two carry outs, right? So we need to combine them somehow. So if you get a carry from somewhere, it should propagate. It should go through and come out on the other end. That's basically what that's saying. So let's just have a look at the logic for that. Here's the half adder. So the half adder was, I think, fairly straightforward. We saw the truth table. You want to verify that it works. So 0 plus 0 is 0 with no carry. 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry, and 1 plus 1 is 0 carry the 1. Then the full adder, you'll notice it's basically just two half adders. 0 plus 1, 1 carry, 1 no carry. 1 plus 0 is 1 no carry. 1 plus 1 is 0 carry the 1. And now we do the same thing with the carry in. So 0 plus 1 is 1 with no carry. 1 plus 0 plus 1 is 0 carry the 1. Remember 2. 1 plus 0 is 0 carry the 1. And then the final one would be 1, 1, 1, which should be 1 carry the 1. Okay. Again, you want to try this out, verify for yourself that it works. Are you able to draw this circuit? Absolutely. You've got Logisim, just draw it, play around with it, try it out. Convince yourself that it does work, and then have a think about what's actually going on, right? So that's the full adder. Full adder is basically two half adders with an extra OR gate to combine the carries. And once we have a full adder, we can actually do addition. How many bits does a full adder work on? 2 bits. It adds 1 bit to another bit. Is that enough? Not even close, right? We want this slide. You'll see how we've got a bunch of full adders glued together. If we have 8 of them glued together like this, and they talk to each other so the carry goes between them, we have an 8-bit addition unit. What kind of machine are you working with at the moment? Is it an 8-bit machine? 64-bit? So probably you have a much bigger addition unit than the ones we're talking about. But the principle remains the same, right? Okay, so we're looking at full adders. So that's the full adder. We also want to do subtraction. So subtraction is a little bit more difficult. All right, and it's a little bit more difficult for a number of reasons. And one reason is we don't want to build a separate subtraction unit. We want to reuse our addition unit. Does that complicate things a bit, do you think? Yeah, it does, because if we just build a subtraction unit, we could just focus on doing subtraction, right? This one has to do both. It has to do addition and subtraction. So here's a diagram, and I'll talk through this diagram. I think this part is fairly interesting. So what we're doing is we have, let's just say we have an addition unit. And now we have an addition unit here, just so we can see the carry going in between them. So that means that this one here is A, and then we've got another A coming in. So I'm going to label this A0 and this one A1, and the next one will be A2 and A3 and A4 and so on, right? We also have a B normally, so the B would normally go in here. Yeah, and this would be B0 and this would be B1. That's right. I just want to undo that little part there and just talk about, well, we're not going to do quite that. What we're going to do instead is, because of this, we're going to use addition, right, to do subtraction. So what we want to do is this, A minus B. We can't actually do that. We're going to have to do A plus minus B. So what do we have to do to B? We have to make it negative in some way, right? Do you remember we did that in our lecture 2 where we flipped the bits? We did 2's complement, flip the bits and add 1, basically that was the process. So we have to simulate here flipping the bits and adding 1. We have to do that process, otherwise it's not going to work. Okay, so how do we do that? So let me just write that down here so we remember that. Flip the bits. So minus B is flip the bits plus 1, right? So we can't just plug B0 in there. That's not going to work because it hasn't been flipped yet. So what do we need to do? Well, the way we solve that problem is we put a gate in the way here. And this is an XOR gate. And we'll do that for each of these guys. And we will put B0 in here, B1 in here, B2 and B3 and B4. And then something else has to go into the other part of this gate. And we're going to put in here something called, and I'm going to call it the sign. There's a separate bit that we're going to add to this thing. Do you notice that we're working with plus and minus? So the sign bit represents what, do you think? 0 is plus, 1 is minus. So if we pump a 0 in here, we want to take just B0 and B1. We don't want to change them, right? Because addition should just work as normal. Correct? If I pump a 1 into this, I'm doing subtraction, and then B0 should be flipped, B1 should be flipped, B2 should be flipped, they should all be flipped. You see they're all connected. The sign bit is all connected to all those XOR gates. And finally, we need to add 1 somehow. Okay, that's a little bit more tricky, but let's have a look at this XOR gate. So how does an XOR gate work? What does it look like? How do you remember the XOR gate? Okay, so the comment was, if they're both the same, it's 0. If they're different, it's 1. Great, yep. You can also just remember the pattern. It's the only pattern that's different from the rest of them. But that absolutely, if they're both the same, 0. If they're different, it's 1. So if I have my truth table here, the sign, and then B, and this is my output, and this is S XOR B. I can draw a truth table for this. So my sign bit, it's going to be a 0 or a 1. Would you agree? Yeah? It's the only two things it can be. So if a sign bit is 0, what can B be? 0 or 1. So my sign bit can be 0 and B is 0, or my sign bit can be 0 and B is 1. What about the other case? My sign bit can be 1 and B is 0, my sign bit can be 1 and B is 1. You notice that I've separated those now. I've drawn a line through the middle, because actually this is the minus case and this is the plus case. In the plus case, what I would like to happen is that S XOR B does nothing. It just leaves B alone. Yep, that's what I want. Now, we'll see whether it does that or not. In the minus case, what do I want S XOR B to do? I want it to flip the bits. Yes? So it should invert whatever B is. Let's have a look at that. 0 XOR 0 is 0. 0 XOR 1 is 1. Well, let's have a look. B is 0, B stays at 0. B is 1, B stays at 1. Did we change B? No, whatever came in went straight through the XOR gate. That's what we were expecting or hoping for. What about the other side when it's negative? 1 XOR 0 is 1, and 1 XOR 1 is 0. So let's look at the output here. B is 0, now it's 1. B is 1, now it's... So what have we done? We've done flip. Whatever B was, we have made it its inverse. We flipped those bits. That's not the end of the story. Why isn't it not the end of the story? Because I flipped the bits, which is fantastic, but I have to still do this. How do I add 1? It's more tricky. Actually, it's really elegant in some ways. Do you remember that there are carries going here? Yeah, there's a carry going between this one, and there's on this side there's a carry in. Yeah? Now the one on the right, we usually don't carry anything in. Why not? Because there's no column there, there's nothing to come in. Yeah? So normally this is just 0, and this one has a carry out. Yeah? So instead of making this 0, let me just plug in the sign bit here. So when the sign bit is 0, what am I adding? 0. When the sign bit is 1, I'm adding 1. That's pretty nice, right? So what we wanted to do with our addition unit is we wanted to kind of modify it a bit so that it also lets us do subtraction. To do that, we needed to implement this, which basically means that we have to take a B and then flip it or invert it. And to do that, we have to flip the bits, which is our XOR gate, and this sign bit, and then we have to add 1, and the 1 is coming from the sign bit. It's actually kind of nice and elegant in some ways. Okay, I just want to be clear, I guess, about this part. What we're looking at the moment is we're looking at a conceptual model of addition and subtraction. In practice, it's not going to work this way. And the reason it's not going to work this way is because there is a delay between this guy working something out, having the carry ready for the next one, and this one being able to accept that carry and update its information. Can you see there's a delay? You have to wait, right? So this is a nice model of it, but the implementation may look a little bit different. Okay, just keep that in mind. So we had a look at subtraction. It gets a little bit complicated, but I think you can see all the pieces that need to fit together and how we made that happen. So in summary for this section, we looked at selection logic, decoder logic, multiplexers, demultiplexers, and half and full adders. And I invite you to have a look at some of this stuff and try making some of this stuff in Logisim and just playing around with it and seeing what the impact is of some changes that you make. So next time, we will look at the arithmetic logic unit, which is a logic unit that also does this addition and subtraction and those kinds of things. We'll look at binary multiplication, division. We'll talk about something called shifting. Then we'll look at sequential logic, and sequential logic is a different kind of logic in some sense, in that it allows us to remember things. So in this situation, what you saw was we get some inputs, we process them, we get an output. We don't remember anything. If we change the inputs, immediately the output changes. That's not always suitable. Sometimes we want memory, so we want to remember things, so we have to build things to make that happen, and it's a little bit more complex to do that. We'll talk about data latches, clocks and synchronization, registers, buses, and the basis of computer memory, and then we'll talk about processors and memory organization. So that's the end of this section.